हेलो माइक टेस्टिंग। हेलो हेलो। हेलो अरुणा मैम। हेलो। एक कैमरा ठीक करो, कैमरा ठीक करो, अरे कैमरा। एक और बताओ। आ रहा है मैम। हेलो हेलो। हेलो 1 2 3। आया आवाज? अरे मोबाइल तो आखिर पंगा होता है तो वो कहाँ से होता है? ये प्रोफाइल यहाँ पे, फाइल यहाँ पे। एक तो वही आता है सिलेक्शन, व्यू, एडिट, फाइल। ये तो दिख रहा होगा। ये हो रहा है। हेलो 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 हेलो। आवाज आ रहा है इसमें? हेलो हेलो। हाँ हाँ हाँ, आ रहा है आवाज। हेलो 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 टेस्ट। हेलो। आ रहे हैं, आ रहे हैं। ओके हेलो मैम, वॉइस आ रही है? चेक चेक चेक। वॉइस वॉइस वॉइस। हेलो 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 स्टूडेंट्स, हेलो हेलो एवरीवन। क्या वॉल्यूम? वॉल्यूम वॉल्यूम। हेलो हेलो हेलो। चेक चेक। मैम यही नॉर्मल वॉइस तो यही रहती है बोलते समय। हेलो। वॉइस स्ट्रेंथ तो मैम यही रहती है। ठीक है, आवाज सही है। आवाज क्लियर? ओके ओके। हेलो 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 स्टूडेंट्स, हेलो एवरीवन। हेलो। ऑडिबल? ओके। We'll start from this numerical solution of ordinary differential equation, right? So here also the point is we want to find a solution of ordinary differential equation, right? We have seen that ordinary differential equations gives us a solution. Let's say y as some function of x, right? We get some arbitrary constant, right? Depending on what is the order of the differential equation, we get some arbitrary constant, and we assign arbitrary constant some value to get a particular solution. So finally the solution comes in the terms of this dependent variable, how it is depending with independent variable. So here also we're looking for a solution of ordinary differential equation. But in this case, we are not going to get a general solution. How we used to get C1 e raised to power 2x plus C2 e raised to power 3x like that. Right here we are going to get a solution for particular input. You give me the value of x, I will give the value of y at that particular location. So in this numerical technique, we are not going to have the general solution as we used to get in my analytical condition, right? Analytical way, right? So here you just give me the value of x, right? I'll give you the value of y, right? This way we will proceed. For a given value of input of x, I'll give you the solution of this y, right? So here we have to find a numerical solution of ordinary differential equation. So let's say this is the x-axis, right? This is the y-axis, and let's say any curve is there like this, right? Some function is there, right? Some function is there, right? Y is equal to f of x, right? So this is a function y is equal to f of x. A function is here, right? Now, or now you see it can be have a solution in terms of y also, right? So some function is coming, right? So now we're going to see how to find a solution. So let's say there is a point over here, right? So here you keep it here like this, dy by dx, some like this. Let's say some point is over here, right? So let's say this is x naught, this is x naught, this certain input x naught at which I will get output, at which I will get output y naught. So this point corresponds to x naught and y naught, right? And let's say we have moved some distance ahead, that is equal to h, that is equal to h. So this h is called a step size, right? This h is called as a step size. We are moving h distance ahead of x naught. So we get another value of x, that is, let's say x1, right? So this x1 corresponds to another output over here, right? This is x1 comma y1, right? This is x1 comma y1, right? Now now so you see here we have this type of curve. Now we have to find a slope of this curve. Let's say I make this way. So this is h and this is, let's say, k. So k is a vertical displacement from y naught. K is a vertical displacement from y naught. So y naught plus k is equal to y1, right? So let's say this is at this point the slope will be calculated by taking tan of this angle, right? Right. So this theta is the inclination of this curve at this point with horizontal. Now let's say we have been given a differential equation as some function of x and y, right? We have been given a differential equation as dy by dx as some function of x and y, right? Now idea is what my objective is here, to find the value of y1. In the question you will be given some initial solution, some initial boundary condition will be given to you, right? At x is equal to x naught, y is equal to y naught. Then they will ask you what is the value of y at particular value of x, right? So they will ask you value of y1 at the x1 input. So they will give you always initial condition, right? X naught, at x naught, what is y naught? and they will give you the value of h also. This is called step size. This is called step size. Right? So this h is nothing but a step size. It's right, step size. How much movement you are making from x naught to reach x1. So logically, if I see x1, if I want to find, x1 is equal to x naught plus h, and y1, if I want to find, y1 is equal to initial point. I already know y naught plus k. So x naught and y naught question will give you, right? Even step size also question will give you. They'll be asking you y1 at particular x1 or y2 at particular x2, right? So the any particular of x, they will want to get the y value, right? So what is the objective? Objective is to know what is k over here, because k will be added to initial output y naught, and you will getting the y1 from there, right? So question will give you x naught, question will give you y naught, question will give you h also. You have to find the value of k, right? We'll see there's some means for how we can find k value. This is a vertical displacement from the initial output, right? That is y naught. Now, right? So if I write tan theta, I know tan theta is nothing but dy by dx, right? And here if I want to find the tan theta, so dy by dx, right? X naught, y naught, right? X naught, y naught. So I'll get a slope. Slope is nothing but tan of the theta. So where I want the slope at x naught, y naught. So I'll put dy by dx, x naught, y naught. This is one thing. Also, I know tan theta is equal to k by h. Tan theta is equal to k by h. So k is equal to h tan theta. Right? K is equal to h tan theta. Right? K is equal to h tan theta. So tan theta will be k by h, perpendicular upon base. So k is equal to h tan theta. Now tan theta of this, I'll put it over here. Right? Tan theta value I know, that is dy by dx x naught at y naught. Right? So I'll find the value of k. So k value here, k value will be, right, h into dy by dx, right, at x naught, y naught. Putting the value of dy by dx here, replacing tan theta. So tan theta will be dy by dx at x naught, y naught. Now dy by dx is what? Some function, let's say of x and y, right? So we have to calculate dy by dx at x naught, y naught. It means if I want to calculate dy by dx at x naught, y naught, you have to put here x naught and y naught, right? Because dy by dx is equal to a function, right? So dy by dx at any particular point you're calculating, it is as good as calculating the function value at x naught, y naught. So here we can write k is equal to h, that is step side, function is there, replace x by x naught, y by y naught. So this is the value of k. This is the value of k. And we are searching for k only because while after getting the k value, I will add to y naught, I will get output at another value of x. So basically I want to calculate y1, right? I want to calculate y1. So just we'll put k value over here. So y1 is equal to y naught plus step size multiplied with the function value at x naught, y naught. So this is very, very important. So you give me the value of y naught, step side, right? And I should know x naught and y naught. So I can calculate the function value of x naught and y naught. I can evaluate y1. So x1 is this, and at that x1, at this x1, y1 is this. And to calculate y1, I need to know y naught and k. And k value is this. this value. So we got this thing. So in general, if I see this in general, right? In general, suppose I have to calculate xn plus 1. So that is equal to xn plus h. I have to calculate yn plus 1. Means and at n1 plus n plus 1 I want to calculate y. So it is nothing but equal to yn plus h step size function value at xn and yn. Right. So this is a general way to express. So with this regard, we have so many ways to calculate the solution. So first method is this, and this is the base method. This is a very basic fundamental method we are discussing. And this method is also called as Euler or forward explicit method. Euler forward or explicit method. So Euler forward method or Euler explicit method. Forward explicit method. So this method is only called as this. So I just put it on here. So I have to calculate y value at n plus 1. That is equal to y at n plus h time function value of xn point and yn. Right. Xn plus 1 is what? That is equal to same thing, right? Xn plus h. The second method is Runge-Kutta second order methods. First is Euler forward method, right? Euler explicit method or forward explicit method. Second is Runge-Kutta second order method. This is also called as modified Euler's method. Modified Euler's method. Modified Euler's method. Right, this also is asked in GATE. So see, the problem is not anything here. Same concept will be keeping over here, right? So I have to find some y1 at some x1. I have to calculate. In my question, always the objective will be to find a solution. Solution you will get when you give the input, right? That is my x1. At this input x1, what is my output y1, right? So they will give you some number. Let's say x is equal to 0.5, x is equal to 0.1. Get me the value of y1. So at this x1, what is my y1? That we have to just find. And the basic concept is same only, right? So here, x1 is equal to, so question will give you some initial condition, that is x0. And with this step size, you will move and come to x1. We will see through problem so, right? And this y1 is equal to y0 plus vertical displacement from y0 to y1. This is the only fundamental thing we have seen in the previous case also. Right? Question will always give you y0 and x0. Some initial condition they will give you. And they will also give you this h. H is nothing but a step size, means how you are moving ahead after each x, right? You are adding h to x naught, you get x1, right? Suppose you want to get x2, suppose you want to get x2, so x2 is equal to, right, x1 plus h, means every time you are going to add this step size to the previous x value to come to the next x value, right? So this is iterative formula. Now to get the value of y1 at x1, I have to calculate this k. Previously we found by different means. Here k will be found in different means. But the idea is same again. We have to use this thing only. So what is k over here? So the iteration formula, right? So first thing we have to find k. So k is what? K is nothing but k1 plus k2 divided by 2, right? And what is k1 for us? K1 is step size h multiply with the function value at x naught and y naught. X naught, y1 naught will be given to you. Function value will be also given to you. Function will be given to you. You have to just evaluate this function at x naught, y naught, right? And then you have to evaluate k2, right? K2 is equal to step size multiply with the function value x naught plus h, right? And y naught plus k1, right? So once you find it out, k1 and k2 like this, calculate the k and put y naught plus k to calculate y1. Right? So here k is calculated by this mean, where k1 and k2 is individually defined by like this, right? So direct we have to use this algorithm to find k and put it over here to find y1, right? So third method also is there, that is called also a Ranjakuta method, but for fourth order method it is called. So third is, right, Ranjakuta fourth order method. Fourth order method. And here also you have the same thing only, right? You have to do the same thing. You will be given x1 value. On this x1 value you have to find y1 value. X1 value can be calculated in terms of known parameter. Some input x0 will be given to you, and you have to add a step size s to come to x1. Y1 is nothing but initial output y0 plus k, right? So in this way you can find value of y1 at this x1. Now the point is, what is k? The k value is given by k1 plus 2 times of k2, right, plus 2 times of k3 plus k4 divided by 6. So here k is evaluated by this method. And what is k1, k2, k3, k4? This you have to keep in mind. K1 is nothing but step size multiply with the function value at x0 and y0. Then we have k2, right? K2 is given by step size multiply with the function value at x0 plus h by 2 and y0 plus k1 by 2. Then k3, right? K3 is given by step size multiply with the function value at x0 plus h by 2 multiply with h by 2 and y0 plus k2 by 2. And then k4. K4 is nothing but step size multiply with the function value at x0 plus h and y0 plus k3. So in this way you have to calculate all these constants. So K4 can be calculated once K3 is calculated, as you can see, right? K3 can be calculated once K2 is calculated because K2 by 2 is here. K2 will be calculated once K1 is calculated because K1 by 2 is there. Once you all know all this, K1, K2, K3, K4, then you can go with this evaluation and put this K over here to get the Y1 at that X1. And then we have the last fourth, right? Euler's backward or implicit method. Euler's backward or Euler's implicit method. Right? So here we have to calculate in this general formula, general way, we have to calculate y at n plus 1 point. So it is equal to yn plus h times function value at when x we are calculating at n1 plus 1 and y is calculating n plus 1. And x is what? Okay, now we see the problem, then we'll get how to get these things. If you see question number 7 in the PDF. Right, so we see question number 7 in the PDF. So we have been given the following differential equation is to be solved numerically by Euler's explicit method. Right, that's the first method. Euler's forward method or Euler's explicit method, same thing. Step size is given 0.1. The solution of for y at x is equal to 0.1. So this is the standard way how the question will be asked. So here you see question number 7 that has been given dy by dx that is equal to, right, x square y minus 1.2 y, right? And see, initial condition is also given. When x is 0, y is 1. When x is 0, y is 1. That's the initial condition. So it means when x naught is 0, y naught is 1. Right? Now what they have given a step size. Which step size we have to use? So step size has been given h is equal to 0.1. 0.1. The step size is 0.1. And also they want to calculate y value when x is 0.1. So when x is 0.1, what is the y value? What is the output? What is the solution? Okay, so we have to see when x is equal to 0.1 come, right? Under what iteration x is equal to 0.1 comes. So see, we have been given by seeing this, we have been given x naught is 0, right? Y naught is equal to 1, which we are discussing. Initial values, initial condition will be given to you. Right, initial some solution will be given to you. With the help of that, we have to move ahead and see in which iteration, in which method, in which trial x is equal to 0.1 comes. Right, so we have to go with that now. So here you see we have this forward explicit method. So here we know that x naught is 0, y naught is 1, and for Euler's explicit method we have this condition. Right, yn plus 1 is equal to yn plus step size multiplied with the function value at xn and yn. Okay. Now, so first thing first, we have to evaluate when this x value comes. First iteration, second iteration, third iteration, when it comes. So let's see, initial x value is known to you. With respect to this, let's see, with respect to this x and using this step size, let's see when I get this value, x is equal to 0.1. So next iteration will be x1. So initial guess has been given, initial solution has been given. I'm keeping as x0. So x1 you will get when you add x0 with the step size given to you. Step size is what? 0.1, right? Right, and x0 is 0. So x0 is 0, this is 0.1. So basically in the next iteration only, right? In the next iteration only I got x1. In the next iteration only I got x1 is equal to 0.1, right? It means in the next iteration y1 will come and y1 will be my answer. In the very next iteration means y0 has been given, the next value will be y1, right? And y1 will be equal to y0 some k, right? So next y1 will be the only answer, because at this x1 only I have to calculate the solution. So at this x1 the solution will be y1. So I have to calculate y1. And y1 will be what? With this thing. So y1 will be equal to y0 plus step size h multiplied with the function value at x0 and y0. Right? Now y0 has been given as 1. Step size has been given 0.1. Now function value you have to calculate at x0, y0. So x0, y0 has been given to me. I have to calculate function value at x0, y0. So dy by dx is some function of x and y, right? This has been given. This is some function of x, y is given. Some function of x and y has been given. X square y minus 1.2y. So put this function value, calculate this function value at this two x and y. So x is equal to 0. This term goes off. So y is equal to 1. So only minus 1.2 will be there. Minus 1.2 will be there. So this thing will come as minus 1.2. Right? And if you solve this, you will get 0.88 as the answer. Right? 0.88 as answer. So this means what? Whenever we are trying to say function value at x0, y0 means replace x by x0, replace y by y0, which is this only we have seen here, and calculate the value of the function value. The function value is coming to be minus 1/2, minus 1.2. Right? This way you get the answer. We'll take next question. Okay. So if you see the next question, question number 8. So we have been given dy by dx as some function of x and y, that is equal to x plus log y. Right? This is what? This is equal to some function of x and y has been given to me, dy by dx. Right? Now, if you see, it is given some condition. Y is equal to 2 when x is equal to 0. So initial condition has been given to me. So when x0 is equal to 0, right? My y0 has been given as 2. So whatever initial condition is there, I will represent by naught, right? x0 and y0. Right? So that is given to me. The solution of this equation we have to find. The solution of this equation we have to find at particular value of x, and that x value is 0.4. And also step size has also given. So h is the step size 0.2, and you have to calculate y value when x is equal to 0.4. The step size is 0.2. You have to calculate the y value when x is equal to 0.4. Now first thing first, you see, to calculate y when this x is there, I have to find at what iteration or what trial this x value will come out to be. when I am going ahead with this step size starting from 0. So let's see the very first iteration. Am I able to get x is equal to 0.4 in the very first iteration? Then I can see what I have to do. So see here, after x naught, I am only able to get x1. x1 is equal to x naught plus this step size. With this step size, you have to move forward, keeping 0.2 plus 0.2 plus 0.2 at every previous x. So x naught is equal to 0, right? H is equal to 0.2. So x1 is what? x1 is equal to 0.2. So it means what? If you try to calculate y1 at this, that won't be the answer. That won't be my answer, because they want to calculate y when x is 0.4. Here in the next iteration, I'm getting x is equal to 0.2. So even if you calculate y1 here, that is not my answer which is they're asking. But still y1 is needed for forward processing. So let us calculate y1 over here. So y1 is equal to y naught plus h multiplied with the function value at x naught and y naught. Right. Now y naught is what? Y naught is equal to 2. H is 0.5. Right. H is 0.2. H is 0.2. Now function value you have to keep when x is replaced by x naught, y is replaced by y naught. So function is this. Get this value when x naught is 0 and y naught is 2. X naught is 0 means x replaced by 0 and y replaced by 2. So log 2 will be there, right? So log 2. So at function value at x naught and y naught is log 2. And when you solve this, you'll get near about 2.138. That is your y1. But this is not my answer, because this y1 is coming when x1 is 0.2. I have to calculate y when x is equal to 0.4. So I have to move further. Next iteration I have to see. We have to see when I will get, in which iteration I will get x is equal to 0.4. At that iteration, I have to calculate y. So this is not my answer, but this is needed for forward processing, right? As we're moving forward and forward, previous values will be required. So x1 I got, right? So now x2 will be what? x2 will be x1 plus h. x1 is what? 0.2. H is also 0.2. So you see we got x2 as 0.4. And at this value only of x, I want to calculate y. It means y2 will be my answer. Right? Because I got that value of x which is asked, on which it is asked y value. So this is x2. What is y2 then? Y2 is nothing but now y1 plus h times function value at x1 and y1. Right. So see, to calculate y2, you need to calculate y1. That's very important notice. Right? Some may be thinking why we are calculating y1 when y1 is not the answer. Because somewhere to calculate y2, you have to calculate a function value when x is replaced by x1 and y is replaced by y1. So in this way, we have to go ahead step by step, and we have to fetch all the intermediate x1 and y1. Right? So to calculate by any y at any intermediate state. Now calculate x1 and y. Now calculate these things. Function value when x is replaced by x1 and y replaced by y1. So y2 is equal to y1 is what? Y1 is 2.138. Step size is 0.2. Now function value you have to calculate. Right? So what you will do? You will replace this x by x1 value, right? That is equal to 0.2, and y with y1 value. That is equal to 2.138. So if you do this, you will get this. That is equal to 0.2 plus log of 2.138. Right? I replace x by x1, y with y1. Now this is the function value. You will get something out of here, and y2 will come out to be 2.33. Right? So this is my answer. So for this value of x2, I got corresponding value of y2. So y2 is my answer. But to calculate y2, y1 is needed, x1 is needed. So we have to go forward by taking every data into the picture. Right, so we'll see next question, ninth question. Now we have been given question number 9. Ordinary differential equation has been given 2y dy by dx is equal to 2y, right? With an initial condition that is given to me, right? And this we got some solution also, right? Solution is given, analytical solution, that is y is equal to e raised to power 2x, right? This we got by analytical solution, right? Even you can get this very easily by variable separation. You can write dy, right, by y, that is equal to dx to 2, integrate both sides, so you'll get log y is equal to 2x, right? Some arbitrary constant, but that constant is not given here, so we'll take it 0. So y is basically e raised to power 2x. So by analytical method, by definite method, by the rules which is present, right, to find the solution, that is method of variable separation, I will get this solution only, right? So question has already given to us, that is not asked to find it out analytically, but I told you this is how we can find analytical method. That is the method, standard method, which is always available in your mathematics, right? But we have to find a solution by numerical method, right? Now, using Runge-Kutta second order method, right? So Runge-Kutta RK second order method I have to use. So question will tell you which method you have to find, which method you have to use to find the solution, right? So we have to calculate y value when x is equal to 0.5. What is the y value? And step size has been given. With this step size, you have to move ahead. And what they're asking, relative percentage error, which you will get. So definitely I told you analytical method is a very different method. You will get the very actual solution, right? Very precise solution. But this method, RK method or any other numerical method, will not give you precise solution. They will give you approximate solution. So definitely the actual solution is this, approx will come from here. There will be some error. There will be error from this to solution. That error will be catch up by this percentage, relative percentage error. Means y value at analytical method, y value by this method, what you will get while placing x is equal to 0.5, and what is the y value when you get by this RK method, that is by numerical, and then you have to evaluate percentage error at x is equal to 0.5. Right? So method is clear to us. So we have been given x naught, right? So we have been given x naught is equal to 0, y naught is equal to 1, right? X naught is equal to 0, y naught is equal to 1. This initial condition will be given to you, because with this initial condition you will actually start. You will add step size to x, you will add k value to y to ultimately reach to your final output. So let's start the next iteration. Let's see which iteration will give me 0.5. Let's see next iteration, what it comes, x1. x1 is equal to x naught plus h. So x naught is basically 0 and h is 0.5. So basically I got in the very first iteration, x1 is equal to 0.5. It means at this value, x1 only I have to find output. So y1 what you will get by next iteration, that will be your answer, right? Because I got the value of x 0.5 in the next iteration, and value of y you have to find at x is equal to 0.5 only. So the y1 will be the answer. Y1 will be what? Y1 will be simply equal to y naught plus k in general, right? For previous Euler forward method, right, k was equal to h times dy by dx at x naught y naught, and x naught y naught, this was given to h multiplied by function value at x naught y naught. So this is the method to calculate k value. But it is said Runge-Kutta second order. So this we cannot apply. This we cannot apply, right? So we have to see the Ranjakutta method. So the arc second order method says get the value of k by k1 plus k2 divided by 2, right, like this. Now k1 is what? K1 is basically step size h multiply with the function value at x naught and y naught, right? So h is basically 0.5 and function value at x naught y naught, right? So here this is divided by dx, right? This is divided by dx, right? So this is divided by dx is equal to some function of y naught, right? So replace x by x naught and y by y naught. Now this is not a function of x, only function of y, right? So y naught is equal to 1. Y naught is equal to 1 over here, right? So y naught is equal to 1. When y naught is equal to 1, f of x or y, f of y is equal to 2 only. So this is equal to 2. Right? This is 2 into 1. That is 2. So that is equal to 1. So k1 is 1. Simply k2 will find. K2 is h times, right? Multiply with x naught plus h, y naught plus k. So what is x naught plus h and y naught plus k? Right? So this is 0.5. So x naught plus x naught was 0, h was 0.5. So replace x by 0.5 and y naught was 1. K we got 1. So this is 2. Replace y by 2. So here there is no scope of putting any x. Just we can put only y value. Okay, we can only put y value. So basically if you put y value 2 over there, you will get 2 into 2, 4. 2 into 2, 4. So function of this is equal to 4. Right? So 0.5 into 4. That is equal to 2. So k1 and k2 we both got. Now I can find k value. So k is value 1 plus 2 by 2. That is 1.5. Right? 3 by 2. This k value I got. Now this k value, how we will use to calculate y1. So y1 is equal to y naught. That is equal to 1. Right? And this is 1.5. Right? So it's equal to 3.5. Right? Y naught is equal to 1. Right? 2.5. So 2.5, sorry. 2.5. Right? So y naught is equal to 1 and k value we got. That is 1.5. Okay. That is a solution. Y1. Y naught 1, k 1.5, 2.5 we got. So at x1 only I want y1 because x1 1.5 we got. So y1 immediately will be my answer. So once I got this, so this is what? This is we got by numerical method. Right? So this y1 we got by numerical method, numerical technique. Right? Another y value you can also get solution. Right? Because y solution is given analytic as y is equal to 2x. Now put x is equal to 0.5. So it is e. Right? X 0.5 half. So it is e. So this you are getting analytic. Right? This you got analytically. Now you can take the percentage error. So y analytic, that is e, right? And numerically it is 2.5 and divided by analytic, that is e, right? So that is, you have to just take the magnitude of this, right? So it is near about 0.8 will come. Yeah, see, the fresh will come. For long iteration, see, we got this, right? So this is one iteration we got the answer. Now K1 we have calculated by this method. This time this time this. So we got Y1, right? Now, in the next iteration, what it will be? You find the new value of K. So for new value of K, you will find new value of K1 and K2. New value of K1 and K2, right? So this initial K1 and K2, it is used to calculate Y1. You have to move more forward. So this will come, this will come. Y1 is equal to, so Y2 is equal to Y0 plus K, right? So Y1 plus K, right? The next iteration. So we get Y1, Y2 here is equal to Y0, sorry, Y1 plus K. So this will be there. So Y1 we have calculated from this here, right? Now you have to calculate the fresh value of K, right? Fresh value of K. So here you have to find here, X0 is done. So you'll replace by X1 and Y1, right? Here X1 plus H and here Y1 plus this K1. Get this point? See, if this iteration goes forward, if this iteration goes forward, so Y1 to already we have calculated. So Y2 we need. So Y2 is equal to, right? Again, previous Y1 plus K. So new value of K you have to find, right? So Y1 you got from the previous things, right? So the K will be what? So again you have to find K. So this new K you can say K1 dash, that is equal to H multiply this function value at X1 and this Y1, because this is already calculated, right? So you will do this. K2 will be what? Right? H time function multiply with X1 plus H, right? And Y1 plus this this is K1 is K2 dash, K2 dash, right? K1 dash, here K1 dash, K1 dash. So you will just repeat again. You will just repeat again. To calculate the next Y2, Y1 is needed that you have calculated from here. You need new value of K. As per this condition, you use the initial condition to come to this Y1. Now for Y2, you use the previous condition, that is X1 and Y1. So H of functional value of X1 and Y1. This is already known to you. Y1 there and X1 also there. Then K2 will be what? Let's say K1 dash and K2 dash. Or let's this being K dash. So K2 dash is again this format. So H multiplied with the function value at X1 plus H, comma Y1 plus K1 dash. This will give you new value of K1 dash and K2 dash, and K dash will be again K1 dash plus K2 dash by 2. So new value of K will come, and that we will put it over here. Get this point? So K will change, K will change depending on K1 and K2, and K1 and K2 value is fixed. For the very first iteration, you have to calculate K1 by taking the very first initial solution given to you. For next, you have to use the just previous data, X1 and Y1, right? Then you will replace X2 and Y2. Like this, you will keep on running with forward, right? So forward method is just like this. Take the previous data, right? Because this is all a modified method only. So forward, you are going, previous data you will keep in hand and you will plug it correspondingly and you will move forward. Right? Okay, so such type of questions are there, right? You have to just use the method properly. Then we see numerical integration. So we can do the integration without knowing the standard way or process to integrate, right? We have the integration to solve some standard look alike integration will come, and we have the proper way to go ahead with that type of problems. But if we get any random complex functions, right, we don't know how to proceed the integration, no rule as such available, so we can go ahead with numerically without going with a definite approach. So now we are not bothered about the function value, not at all. Whatever complex function comes, let us come, we are doing numerically. So we are not bothered about the approach, a standard analytical approach to solve. Only we have to see that how we are breaking up the function, right? So here you see we have three approach to solve integration by numerical method. First is trapezoidal method or trapezoidal rule. Okay. Just a sec, we'll start again. So first method is trapezoidal rule. Trapezoidal rule. Second method is Simpson's rule. Simpson's rule. Right, or Simpson's 1/3 rule. Actually, it is called Simpson's rules also. So let me write first in this way: Simpson's 1/3 rule, 1/3 rule. And the last is Simpson's 3/8 rule. Right. Now see, when question will come, question will sometimes they will tell you which rule they want to ask in Simpson. Right, name is same. Right, so they will explicitly write Simpson's 1/3 rule or 3/8 rule. And sometimes question does not write which rule they're asking, right? So sometimes question writes Simpson's rule with Simpson's rule or with Simpson method, right? So if nothing is method, nothing is mentioned, that is only 1/3 rule only, right? This is also called, if nothing mentioned, so you have to use this Simpson. Right? Use this. If nothing mentioned, 1/3 or 3/8. If nothing is mentioned, Just they have mentioned Simpson's rule. So you can write this is also nothing but simple straight away Simpson's rule also. Simpson's rule. If simple blank Simpson's rule is there, it means 1/3 rule only it is conveying to you. Otherwise, they write many times 1/3 or 3/8. So what is the way to calculate integration? See, we will be given some function to which we have to integrate with the, let's say, variable x from lower limit, let's say a, to upper limit, let's say b, right? So let's say initial point is x naught from a, and final point, some nth point is b, xn is equal to b, right? So here we have to integrate from lower limit a to upper limit b. That's how integration is done. But this complex function is very typical, very typical. We don't know how to proceed, right? By using any trigonometric or log, any rule. So we have to go with some another method. The method is we will break this lower limit and upper limit into some equal interval, right? Into some equal interval, we'll break this lower and upper limit. So, and that will bring the step size. So h, it will come over here. This is called interval size or step size. Or step size. So we'll break this upper and lower limit with some equal intervals. How many equal intervals? That question will tell you. Question will hint you, right? We don't have to bother. So this how we can break h. This step size is nothing but final limit minus lower limit divided by n. N is nothing but the equal number of intervals. Right. So this n is nothing but equal number of intervals. Right. So total span is b minus a. You are dividing with this number of equal intervals. So how much you have to go ahead every step? H, right? So how many equal intervals you have to divide by upper and lower limit? Question will tell you. Question will give you what? Question will just give you this function. Question will give you this function. They will give you, right? They will give you lower limit. They will give you upper limit, right? And also they will hint you directly, indirectly, what number of equal interval you have to break, right? So you can calculate h by this method, right? H by this method. So we want the value of h, step size, right? From here. With so many data, we can solve integration very easily, right? So let's say first method is trapezoidal method. First method is trapezoidal method. Right? Suppose we have a x-axis over here, right? We have a x-axis over here, and any function is here, right? Any function is over here. Any continuous function f of x is there. Right? We have to integrate this. We have to integrate this from some, let's say, lower limit a, right? Lower limit a, right? Lower limit a to the final limit b. Right? That's what it was given. Lower limit a to final limit b. We have to integrate. So first thing first, a correspond to what value on function? Right? We have to see here, right? So let's say y naught, because this a is nothing but x naught. A is equal to x naught, right? So it will correspond to some y naught. So it will correspond to this y naught, right? And this is any xn, any nth point on my x. So this will correspond to yn, right? Now a and b, this is such a large size. I will break my this total limit into equal number of interval. How? B minus a. And what is the desire of the question or from the examiner? They will tell you in how many equal interval you have to divide. Means hold this limit you are dividing into some equal intervals, right? So see here, let's say this is one equal interval, this is another equal interval, right? This is another equal interval, this is another, this is another. Okay, some equal interval we have divided. So let's say this is x1, this is x1, this corresponds to y1, right? Let's say this is x2, this corresponds to y2, this is x3, this corresponds to y3, this is x4, this corresponds to y4, this is x5, y5. So like this we can break this by total span from A to B with some equal interval. So these are sharing equal gap, right? This is h, right? This is also h. What is h? We can easily calculate. So each interval is of same size. That is the value of h. Right? Now, if you want to integrate by this method, now this method is suitable for linear function. Remember, right? This method is suitable for linear function. Let me write here. Trapezoidal method is suitable for linear function of x. For linear function of x. Right? That is 1 degree polynomial or degree 1 polynomial. This method is suitable for linear function of x, that is degree 1 polynomial. Means if this is a function which could have been linear function, I would have got trapezoidal method the best method to solve. So error will be reduced. Right? You can use it in any type of function, right? But the error will be more. Error, if you want to reduce or make it to minimize, so you have to use this trapezoidal method for the linear function of x. So this integration f of x dx from A to B has been given by trapezoidal method as this: h by 2, right? Y naught plus yn plus 2 times y1 plus y2 plus y3, like this, yn minus 1. So this integration is performed by taking 2 points, any 2 points on the curve, and drawing a line. Suppose I have 1 point y naught and 1 point y1. So trapezoidal says that this basically rule is applicable when it's a linear function. So it will not connect this y1 and y0 along this curve, rather straight it will just connect, right? Then y1 and y2 will be straight connect like this. Then y2 and y3 it will be also straightly connect. Then y3 and y4 also they will straight connect. Simply for y4 and y5, right? Like this y5 to ynth. So basically trapezoidal methods involves connecting 2 points, right, by straight line, because this is basically applicable for linear function of x. Linear function of x means straight line only, straight line. So all the points are connected by a straight line, and then it has been formed a trapezium. As you can see, this is a trapezium, this is one trapezium, this is another trapezium, this is third trapezium, fourth trapezium. Like this, so many trapeziums are there. I'm just calculating the trapezium area and just adding up and to get the integration under this curve, because integration means area under the curve. Integration means area under the curve only. So area under the curve, you see here, will get under the yellow color curve. But you see, we are connecting 2 points on this curve by a straight line. So definitely all the area you cannot cover. Some area is left over here, some area left over here, some area you are taking more over the yellow color curve. Some area is left, some area is left, some area you are taking more above the yellow color curve. So there will be some error. There will be some error if your function is basically 2 degree, 3 degree, 4 degree polynomial. But if it is a totally a straight line, then you are connecting 2 points. Anything on the straight line, it will be just superimposed on the straight line only. So error will be zero or error will be minimized. Right. So here we are taking 2 points on the curve and connecting with a straight line, we get a trapezium. And we are adding the trapezium area only to get this. So this is just adding the trapezium area to get the integration, because integration when we do, we get the area under the curve. So here we're getting the area under this trapezium. So collect all the area under this trapezium, which you have straight away got by connecting 2 points by a straight line. So this will give integration of this function with respect to x. But error we can see because it is not a straight line curve, it's some n degree polynomial is there. So yellow color may be going above the straight line, below the straight line, above the straight line, below the straight line. So some area will be always left over. You will not be able to collect that area. So the integration by this method will be showing lot of error. But suppose this is a straight line only. A straight line, this yellow curve is a straight line only, like this, right? Then you will get this trapezoidal method, the best method to perform for the integration, right? Then we have a Simpson's 1/3 rule. Simpson's 1/3 rule. This is give you accuracy for 2 degree polynomial. Accurate for 2 degree polynomial or quadratic equation. Just remember, if it is a 2 degree polynomial, then you should integrate with respect to Simpson's 1/3 rule. Or if it's a quadratic equation, you should integrate with respect to Simpson's 1/3 rule. Right? And it says that if it is f of x dx from a to b, that is equal to, that is equal to h by 3, right? Y naught plus yn, right? Y naught is the output at initial lower limit, yn is the output at the upper limit, plus 4 times, right? Y1 plus y3 plus y5, like this it goes on, right? Plus 2 times of y2 plus y4 plus y6, like that this goes on. So 4 times multiply with y1 plus y3 plus y5, the odd parts. And even parts are multiplied with 2, y2 plus y4 plus y6. With the problem only we'll get how to resolve this, but it's a very simple thing. So last is Simpson's